Okay, good day, everyone. Today we are beginning our lecture recording on SEM 4312, which is Embedded Software Engineering. This course is for 400 level software engineering at Kala University, Katsina, for first semester 2022-2023 academic section. As you might know, we were directed by the management to commence lecture, even though you are away on CWES and you may likely be engaging you may likely be on break during this election period. This is because we want to utilize the time to make sure we cover something substantial before we resume physically on campus, and then we carry on with other academic activities. My name is Dr. Armaya'u and I'm the course lecturer for this course. So first and foremost, we begin with the course outline. I always remind you that the main point of giving students course outline is for them to go ahead of the class and explore on their own. That is for those students who have extra motivation. It's always good if you can read ahead of the class. So when we come to lecture, so you realize you only need clarification on certain areas. And even if you want to ask questions, you may likely ask more relevant questions and more important questions if you like. But first and foremost, we are going to look at the brief overview of what embedded systems is, or what embedded systems are their examples. And then we're going to look at hardware component of the embedded system. Then next we are going to look at software component of the embedded system. Then we look at the design process of software for embedded system. We'll particularly pay attention to some category of embedded system that have a real-time constraint, which means these systems they interact with physical environment, and the software or the component of the embedded system has to act within some time constraint. Then we look at the basic embedded system software development. So beginning with the definition. So we look at two definitions. The number one is from Giovanni Di Marcelli, who is an Italian, and he's an electrical engineer, but with extensive experience in embedded system design and development. He defines embedded system as a digital system that provides services as part of a larger system. Another definition is from Peter Maweda. He's also an embedded system researcher and an expert. So he defines embedded system as embedded systems information processing system embedded into a larger product. Why I'm quoting these people and briefly telling you about their profile, because students nowadays they have a habit of going online and maybe collect some information that can be described as garbage. And sometimes they acquire some mindset and they begin to think, okay, what they read is right. So we are saying, yeah, it's okay to explore on your own and or whatever you want to use to find information, but make sure those people that put the information there, they are authorities in their field. So it's possible to go and just somebody, because he has access to internet and maybe has a blog or whatever, and then the red is decided to rubbish, and then you can consume rubbish, and you begin to acquire a mindset that is not on what is actually right. So we have a few examples of embedded system, beginning from electronic toy. And here is the usual mobile handset. These are set-top boxes, and this is electronic control unit, which is known here in Nigeria as brain box of the car. This is your normal decoders, but actually their names are called set-top boxes. And this is a smartwatch, and this is smart TV. So going by definition, you agree with me, all these devices, they have certain software functionality embedded with them. But actually, if you look at this word, larger system, larger here is relative. because some of these systems are not really large. But the main point here is that software or embedded system software or the software and hardware, they are not really standing alone on their own, but they are rather part of uh, another system or another product. We have more specific examples for some specific domain, beginning from automotive. We have different sets of embedded system in that domain. It's usually said a modern car is equipped with millions lines of code in them. For example, if you look at anti-locking braking system, otherwise known as ABS, which is actually a software mechanism that stops car from skidding. It's also an embedded system because it's embedded within a car itself. We also have ESP, which is electronic stability control. It's also prevent car from skidding. The only difference is the ABS is applied when the hard brake is applied. And we have airbags, efficient automatic gearboxes, theft prevention with smart keys, that's securities that are being uh, deployed on cars. We have blind angle alert system. So here is an embedded system that modern cars are equipped with, and they actually use cameras and sensors to detect if a car is moving towards an object. This is actually covers the areas that are not visible by the driver. We have in-car entertainment system, and those uh, entertainment or infotainment system that the modern cars are equipped with. So all of these they exist in a computer in a car because they will have to be networked. So there has multiple networks, and mostly microcontrollers or processors are being networked in order to make them communicate and achieve a common goal. We have another example in bionic domain. We have flight control system and collision system. This is actually uh, just like the way blind angle alert system in cars operate, and collision systems use radar to detect moving aircraft so that two aircraft will not collide each other. Um, Again, pilot information system, it's a unit in an aircraft equipped with so many information about moving aircraft. And even power supply system of an aircraft is somehow has embedded system. And we also have systems such as flight control. So you agree with me in all of this, maybe with the exception of a car entertainment system, these kind of systems, they require utmost dependability because it's a matter of life and death. So any slight mistake, if a software or embedded system fail, I can claim lives. So we here in this slide, we try to depict a comparison between embedded system and a generic system, or rather a standalone system, in terms of certain consideration. The first consideration is functionality. How much function does embedded system covers? Mostly they target specific function, and this is not really as generic as such a standalone system. But they cover a very tiny application area. And in terms of flexibility, the embedded systems have limited flexibility in such a way that application cannot be installed and uninstalled at will, as in generic system, because they have the firmware that control the hardware devices, and those firmware are already pre-programmed. And the only thing is they can support, the only flexibility they can support is what is called field programmability or over the air update. Over the air update means for some kind of system to acquire update of the firmware or other application over the air without physically connecting those devices to a server where they will download the software. And there can be also what is known as field programmability. that is being able to program an embedded system while it's in operation. And next is performance. Of course, performance is generally desirable in all kind of software system, but it's more so in embedded system because some of this system can be mission critical. So the application need to take action based on certain uh, value, maybe read from sensors right there and then. I'm missing even 1 millisecond. Then but most systems that are not embedded, the response requirement are not time critical, so maybe you can miss a deadline, 1 minute, 2 minutes, or even 10 minutes, and nothing will happen. You only be disappointed in that the system has not been responding the way it should. But in embedded system, it can claim lives. This is similar to the last consideration, which is reliability. That is, execution behavior is deterministic. We want to be sure that this system must be executed in the way it's meant to be. That's why there are so many analyses that are done for embedded system specification. But for generic system, uh, the behavior of those systems are not completely deterministic. It means a software can can have some spaces that are not really covered in the specification and couldn't actually predict how it will operate. But for embedded system, all the possible operation scenario of that software must be specified and studied before it's developed. So the software in embedded system has to be deterministic. So looking at the very briefly the hardware, we are going to have a topic on hardware. So here we are just maybe giving you an overview of what typical hardware in a system. So it typically consists of microcontroller or microprocessor along with other hardware components of technology. So yeah, if it is a microprocessor, it might be microprocessor, and outside that microprocessor there are memory and other I/O interfaces. But usually microcontrollers they have those additional peripherals with them. So that's why they are called microcontrollers. And for example, modern cars they may have many microcontrollers and each one specialized in doing certain things. And that's why they will have to be networked in order to achieve the overall goal of their existence. Uh, Again, we can classify embedded system into real-time, soft real-time system. As I said initially, missing deadline may not be critical and can be tolerated for a certain degree. For example, when you have, let's say, what we call it, Beaver's machine, whether the machine responds by placing a finger on it the next minute or next 5 minutes wouldn't matter much. Of course, they play some, but how about if airbag refused to go off or failed to go off for 1 minute when it's needed the most? So you see, so these are called hard real-time system, but because they need to respond uh, in the time they are meant to respond. And even the delay of 1 second can be deadly. So why do we study embedded system? This is a kind of motivation. Why do we even need to study? Yeah, so one of the reason is PC era. That is, it has been prophesied that in the near future, I believe the future is already there, that computing will become ubiquitous and pervasive. That is, the computers uh, will be integrated into everyday life. That is into even tiny products, so that they will even become invisible because of the way they are integrated in many aspects of our life. And again, this also including ambient intelligence, where we need a lot of sensors to gather some information and analyze data. And again, some problems can only be solved with better software. Because now, if you look at the beavers, for example, uh, of course, students tend to say, okay, we are developing online application for students to cast their vote. But looking at the Nigerian demography, you see that you cannot deploy like a server, a remote server, and say, okay, we are trying to online vote. So the best solution at the moment is to deploy these devices which carries embedded software in them. So, and again, because you cannot develop embedded systems anyhow. Why? Because they have additional constraints and challenges. They don't have power or energy. They are not always connected. That is the assumption. They can go out without even power for hours, maybe for days. And dependability, we've seen how missing or an error in embedded system can be deadly. So we want embedded system to be dependable. And that's why they will have to be studied. And real time processing, some information need to process and act on real time. Yes, some embedded systems are mission critical. And again, for the developed economies, so you realize most of the software is even 90 or more than that of software are being developed for embedded systems. This is because they produce products. But for the developing economies, mostly the software we develop, they are not embedded products that needs software in them. So again, this is one of the motivations why we study embedded systems, because when systems that are meant to be engineered are under-engineered or not engineered. One example is Toyota unintended acceleration. That was Toyota Camry 2005. It was accelerating for no reason, and it's discovered that it was a bug software. So this is the highlights of the findings from the Commission of Inquiry. It reads that there are C sources for which there are no specification documents. Okay, if you remember our course, our last semester course on software architecture, we can see there was unfaithful implementation of the software because some code exists, but they didn't have specification in the architecture. And then they say specification document and C do not correspond one-to-one. Yeah, there is no mapping from the architecture and the implementation. So you realize the implementation specify, okay, need to be C, but the implementation implemented A, B, and D. And they said when they were conducting the investigation, they realized or they found the company was already into activities in the spaghetti-like status of engine control application. That is the software code resemble the way spaghetti is. It's tangled all over, which is a problem for some time maintainability. Yeah, and there was also a bug for thermostat by a company called Nest UK. This is actually a product that controls the heating of houses. So it determines the appropriate temperature to heat the house. And when they actually deploy them, they were happy because they could save a lot of costs from maybe leaving gas to run uncontrollably. Again, one of the under-engineered embedded system was Airbus software misconfiguration, which resulted in crash of airplanes sometime in 2009. And again, the committee of investigation found that, of course, although there was no structural defect, but there was serious quality problem in the final assembly. The error was not in the code itself, but in the configuration setting. So you see, all these things points to why we should study embedded systems so that we can maybe engineer them properly to avoid disastrous consequences. That is the end of this lecture. So maybe within this week, we'll try and see if I can record another video. I mean, hardware component of embedded system.